Hey everybody, this is Jake Spencer, and today I'm going to be discussing Chapter 5.3, which is all about enthalpy. So what is enthalpy? Chemical and physical changes that occur around us every day, such as photosynthesis, or like evaporation of water, or even like our lab experiments, occur under the essentially constant pressure of Earth's atmosphere. So these physical and chemical changes result in the release or the absorption of heat and can be accompanied by work done by or on the system. When taking a look at these changes, it's useful to have a thermodynamic function that is a state function and relates to the flow of heat or energy. Under conditions of constant pressure or atmospheric pressure, a thermodynamic quantity, which we call enthalpy, provides such a function. So enthalpy, which is denoted by the letter H, is the internal energy plus the product of the pressure P and volume V of the system. So the definition of enthalpy is literally this equation. It's energy plus pressure times volume. And remember from our previous units that energy, pressure, and volume are all state functions, which means that they depend only on the current state of the system and not on the path taken to that state. So because all of these are state functions, that means that enthalpy is also a state function. Kind of changing gears a little bit, another important piece of this chapter is pressure volume, or PV work. So PV work is work done specifically in constant pressure with the expansion or compression of gases. So this visual right here provides a good indicator of what like PV work looks like. So in this reaction, we have solid zinc being dumped into hydrochloric acid. So the zinc solid is reacting with the aqueous hydrogen ions to form aqueous zinc ions and hydrogen gas. So assuming that within this vessel it's constant pressure, as the reaction comes to completion and forms more hydrogen gas, the piston in the top of the vessel begins to move up, which means that the system is doing pressure volume work. And one way to calculate this PV work is this equation up in the top right, which is W equals negative P, or pressure, times delta V, which is the change in volume. Or basically, in this example, how much the piston moves up. That's going to be the delta V. How much volume the piston moving creates. And in order to calculate delta V, it's the volume of the final versus the volume of the initial. And typically when we're doing this equation, pressure is going to be measured in atmospheres, while volume is in liters, which creates this weird unit, but one useful conversion factor when doing PV work is 1 liter times atmosphere equals 101.3 joules, which is a much more comfortable and common unit. So let's take a look at this example of PV work. A fuel is burned in a cylinder equipped with a piston, just like we saw here. The initial volume of the cylinder is 0.250 liters, and the final volume is 0.98 liters. If the piston expands at a constant pressure of 1.35 atmospheres, how much work in joules is done? So right off the bat, this is obviously a PV work question, and it's going to be using this equation we have right here, because it specifically denotes that we have a constant pressure of 1.35, and it gives us the final volume, which is 0.98, and the initial volume, which is 0.25. So they're giving us everything we need. We just have to first calculate the delta V, which is easy. You just take the 0.98 liters, which is the final, minus the 0.25 liters, which is the initial, and we're left with the delta V being 0.73 liters. And then after that, we just have to plug it right into the PV work equation. So we have negative 1.35 atmospheres, which is the pressure, times the delta V, which is 0.73 liters, which leaves us with negative 0.9855 liters times atmospheres. And using this conversion factor that we discussed in the previous slide, we can use dimensional analysis, which leaves us with negative 99.8 joules, which is how much work is done in the system. Going back to the discussion of enthalpy, when a change occurs at constant pressure, such as like PV work, the change in enthalpy, which is denoted by delta H, is given by the relationship delta E plus the product of P times delta V, assuming it's constant pressure. So that is the change in enthalpy equals the change in internal energy plus the product of P and delta V. If you recall from earlier chapters, we know that the change in energy, or delta E, equals Q plus W. And just like we looked at earlier, P times delta V is equivalent to negative W. So we could actually rewrite this equation as delta H equals Q plus W minus W. And that a subscript on the Q in here is just to represent that the system is, or the reaction is happening under constant pressure. So Q plus W minus W equals Q. So under constant pressure, delta H is actually equivalent to the heat, which is gained or lost by the system. So how can we apply this? If delta H and Q are equivalent to each other, and we know that when heat, aka Q, is lost by a system, it's considered exothermic, and when heat, Q, is gained by a system, it's endothermic. We're going to keep that in mind for this example coming up here. So in this example, we're going to want to indicate the sign of the enthalpy change, delta H, in the following processes carried out under atmospheric pressure or constant pressure, and indicate whether each process is endothermic or exothermic. So because it's under atmospheric pressure constantly, delta H is going to equal Q, just like we determined on the previous slide. So if the reaction is endothermic and is gaining energy, that means Q is going to be positive, and delta H is also going to be positive. And on the other side of things, if a reaction is exothermic, Q is going to be negative, which means delta H is also going to be negative. So these two examples, when an ice cube melts, in this reaction, the system is gaining energy because the ice cube requires energy and it needs to gain heat in order to melt. And then for this reaction in part B, it's a combustion reaction, which immediately off the top of your head is going to be exothermic, because combustion reactions always release energy or heat. So that reaction is going to be exothermic, which means the ice cube melting is endothermic, which means delta H is going to be positive. Meanwhile, the combustion reaction is exothermic, which means delta H is going to be negative. But yeah, that's about it for this chapter. Pretty simple, but also some very useful concepts when it comes to like state functions and thermodynamics as a whole. You're going to see a lot of delta H in thermodynamics, so this is a good way to kind of set the ground. But anyways, that's going to be all for me. Thank you guys so much for watching, and good luck on your AP exams.